All right, we have another ChemCatalyst today. It's going to be just like yesterday's. All this week, we're going to kind of keep these ChemCatalysts practicing finding those conjugate acids and conjugate bases. All right, that's going to be your mini quiz right when I get back, so we might as well get as much practice in as we can. Once you start noticing these patterns, again, I really think you guys are going to get the hang of it. So take some time, copy this in your notebooks. Please try them on your own. If you just keep copying down the answers from these slides, then you're not going to get a lot out of this, all right? And you're not going to be ready for that quiz on Monday. So make sure you try them on your own first, see how you do, and then if you have questions, of course, go back and watch the video. All right, pause it now, and I'll show you the solutions here in a second. All right, so remember for Bronsted-Lowry, we're wanting to really focus on those definitions for acids and bases. All right, they all have to do with the transfer of a proton, or H+. All right, acids have an H+ that they can donate. So we say they donate or lose H+, all right, or a proton. Bases are able to accept protons or accept H+. All right, so they're going to gain an extra H+ when they become their conjugate. All right, so again, just like yesterday, numbers 1 and 2, all right, are both starting out as acids because they want you to find the conjugate base. All right, so HF, hydrofluoric acid, they want you to find its conjugate base. So again, it's going to lose its H+. When it loses H+, all that's left over is fluorine with a 1- charge, all right? Or you can just write a negative sign if it's 1-, that's fine, all right? For H2CO3, we want to remember it's a little different from when we had the diprotic acids in Arrhenius definition, all right? In a diprotic one, we would just lose all the hydrogens for an acid-base reaction. For Bronsted-Lowry, we only lose one at a time. So we're not going to lose both of these H+. We're only going to lose one of them, all right? So when you become a base, we're still going to have one hydrogen left over, plus the CO3, all right? But we lost a positive charge, so it's going to become a 1- charge instead, all right? So be careful of that. You're only losing one H+ at a time, or if you're a base, you're only gaining one H+ at a time, all right? So for 3 and 4, it wants you to find the conjugate acid, meaning these are already the bases, all right? Cn- is your first one. So if we were to add an H+ to it, like it would if it was a base, it's going to gain an H, all right? So you have HCN. And then again, remember it has a positive 1 charge. So if we add a positive charge to a 1- charge, it's just going to become neutral. So we don't need to put anything as a charge there. All right, very similar for this one. We have HS, so there's already one H there, one hydrogen there, but there's a -1 charge. So when we add another H+, all right, we're going to have 2 hydrogens instead, and the positive 1 charge from the hydrogen that we added cancels out the negative charge that we started out with. So we just have H2S for our final answer. All right, go ahead. Pause, get ready to start some new notes today, all right? Definitely watch the video and kind of follow along as we get started on our calculations that go with this chapter. All right, so hopefully in front of you you're looking at this chart that says we're comparing a few different things. So take a second to kind of take that in. There's a few different things going on. So one is that we're looking at a molarity, which again means concentration, all right? So concentration or molarity, molarity is just a unit of concentration, all right? So concentration, for some of these, it's HCl, so hydrochloric acid for the first half, all right? Here in the middle, we have water, which is not a solution, so there's not going to be a concentration there. All right, it's just plain old water. And then at the bottom we have some NaOH. All right, some sodium hydroxide, which remember is our strong base. All right, so up here you can kind of see it starts out a pretty high concentration. We get lower and lower and lower until we're basically so diluted we might as well just be water. So it switches over to water. all right? Then we start out with very diluted sodium hydroxide, and it slowly becomes more and more concentrated until you get to 1 molar there at the bottom. All right, so that's the first column. These second two, all right, we have this H plus in brackets and OH minus in brackets. So a hydrogen ion in brackets and a hydroxide ion in brackets. Make sure you make a note of this. If you see anything that's in brackets, so those kind of angled, square looking parentheses, all right, if it's in brackets, this means concentration of, all right, or molarity for you guys. Okay, concentration or molarity of whatever's in the brackets. Okay, so if it's H plus that's inside of the brackets, then it's the concentration of H plus. If it's OH minus that's in the brackets, then it's the concentration of OH minus. If it was HCl in the brackets, then it'd be the concentration of that hydrochloric acid. So the brackets just mean what's the concentration of it, or another word, the molarity of it. Okay, so you can kind of see that when we go down, H plus concentrations here as we go down, all right, and OH minus concentrations or molarities as we go down, all right. Notice the exponents here on the tens. These are all written in scientific notation. For H plus, they become increasingly negative, meaning they get smaller, all right. So the H plus concentration is decreasing as we go down this chart, all right, until we hit the lowest one down here. All right, for OH minus, it's the exact opposite. You can kind of see they're like a mirror image of one another, but just exactly flipped. All right, here we start out with the highest exponent. We get more negative as we go up. So in this case, actually, the smallest or lowest OH minus concentration is at the top of the chart, and then it gets higher and higher and higher and higher until you're the most OH minus concentration down at the bottom. All right, we'll talk about that in a second. All right, this last column, these are those pH values. So this is what we saw with the universal indicator. So these are the numbers that went with those colors from the universal indicator in your lab. All right, so if it was red, it had a low number. If it was purple, it had a high number. All right, so you can kind of see these values are getting higher and higher and higher as you go up. So some things we can kind of take away. Let's look at just general trends first before we dive right into the math. All right, some things I want you to notice right away. First of all, is that the HCl concentration, like we've said before, is going to be the same as the H plus concentration. Remember, if it's in brackets, that means concentration. All right, these two numbers are always the same when you look side by side. In this case, the only difference is that the HCl concentrations are written in standard notation, so just like 0.01, all right, versus the H plus concentrations are written in scientific notation. But those two numbers are exactly the same thing. If you put 1 times 10 to the negative 2 in your calculator, you're going to get 0.01. All right, it's just two different ways of writing the same number. All right. The second thing I want you to notice, all right, very similar, is that the concentration of NaOH, sodium hydroxide, a strong base, is the same as OH minus concentration, hydroxide concentration. Okay, so again, if you look down here, if you look at some of these numbers down here, all right, we have another 0.01 molar NaOH. If you look over at the hydroxide concentration, again, it's the same number, just written in scientific notation. That's the only difference, all right? But they're exactly the same value. There's no actual difference when you put it in your calculator, okay? So that's the first thing, all right? Pretty easy. Second thing we want to look at is that for our acid, so for hydrochloric acid, and this is also going to go for any acidic solution, not just hydrochloric acid, all right? The concentration of H plus when it's an acid is greater than the concentration of OH minus. All right, so if you look at all the numbers, when we're in this top half of the table, all right, with hydrochloric acid, all of these numbers are larger than the numbers in this column. All right, all of them. All right, the opposite's true for hydroxide, for sodium hydroxide. all right? If you're a base or any other basic solution, doesn't have to be sodium hydroxide, then you're going to have a higher OH minus concentration. All right, this should make sense because this is kind of what Arrhenius, the first definition of acids and bases, said. All right, it said that OH minus was more common in basic solutions, H plus more common in acidic solutions. This is kind of reaffirming something you already knew. All right, you should notice when we have something like water, something that we know is not an acid or a base, all right, something that's neutral. All right, these two concentrations are exactly the same. All right, so these are equal to one another when it's a neutral solution. And even on here, you can see right above it, so these ones right here above it and right below it, we have acids and bases that are so diluted. There's so much water in there compared to the acids and bases that are in there that it's basically as if it's water. All right, it's basically neutral because it's so watered down. So that's possible as well. All right, other things we should look into. All right, let's look at the pH column because this is kind of the new thing and this is what we're going to eventually have to be able to calculate. So let's look at some things we can tell based on this pH column. All right, so one thing we should notice as the pH value goes up, so basically as we go down this table, all right, as the pH value gets higher, all right, we're definitely becoming more basic. Hopefully that's obvious to you by now. We're becoming less acidic and more basic. So some things that would mean, all right, as the pH value goes up, all right, that means we're becoming less acidic, so our H plus concentration is going to go down, all right? We're becoming more basic, so our OH minus concentration is increasing, and these are things we pointed out right at the very beginning, all right? Along with that, hopefully you're kind of aware of some other things, or maybe you're even noticing some of these numbers have some special kind of things going on. So not only does the hydroxide concentration increase as we go down the periodic table, but down this table, all right, and the H plus concentration decreases. But if you look at the numbers, all right, look at the numbers themselves. There's some pretty special things that are happening. So, for example, let's look at particularly the H plus column, and then again this pH column. All right. Take a second, even pause the video if you want, and see if you can see any similarities or any maybe connection to those two columns, the numbers themselves. So focus on actually the values, not just, oh, it got bigger, it got smaller, but look at the numbers themselves. All right, so I'll hold off for a second, but see if you can find a connection here. All right, hopefully, other than a couple exceptions, so we've got kind of like a weird one here, and we've got a weird one here, all right? But hopefully, other than those couple weird exceptions, all right, if you look at the exponent, all right, so look at the exponent of the scientific notation number, all right? If you look at these, all right, I should have skipped this one, sorry about that. All right, if you look at these, okay, all the way down the table and compare them to the pH values, hopefully you're seeing what I'm saying now. All right, 10 to some power, all right, if in this case it's like a -1, the pH value is going to be a 1. If it's 10 to the -4, the pH value is a 4. And this is the case all the way down, even 10 to the -9. The pH value is 9. And that's how we're going to come up with our equation for how we calculate a pH. All right? For those of you who have had logs before in your math classes, this shouldn't be too bad. This should be actually pretty easy. If you haven't had something called logs before in a math class, then this might be a little bit weird, but the good news is you get to use your calculator and you don't have to be able to do these by hand. All right, so we'll kind of learn what that means here in a second. Okay, so now that we've at least seen a little bit about the value of pH and kind of how it relates, especially to the concentration of hydrogen ions or protons, okay, H plus. Now we're ready for the math part, all right? And so I'm going to try and simplify it as much as possible. We won't get too intense with it, but there is some math that goes along with this unit, and so I want to make sure you guys are ready to go on that when I get back. So the two equations you see right now, these are the two main ones you need to know how to use, all right? The first one, all right, relates the hydrogen ion concentration to the hydroxide concentration. So we already talked about the fact that as one gets higher, the other gets lower. All right, for acids, H plus is higher. For bases, OH minus is higher. All right, but this is the equation that actually allows you to calculate those values. So if you know what the concentration of H plus is, then you can plug it in here where it says this brackets H plus concentration, all right, and then solve for the OH minus concentration. So it's just H plus times OH minus is equal to this constant value, all right. Under normal circumstances, it's equal to 1 times 10 to the negative 14th, okay? These are concentrations that you're calculating, so you want to make sure your unit is molarity, capital M, but we'll kind of practice that later, okay? So that's the first main equation, all right? And that comes from this idea that in every solution, there's going to be at least some of both of those ions. Even in water, normal old H2O, all right, there's always going to be at least a little bit of H plus and OH minus, because that's what water is made up of. It's made up of H plus and OH minus, hydrogen and hydroxide. All right. Now, usually it's not very obvious. There's so little of it. All right. We're talking, again, 1 times 10 to the negative 7 molar from that table. It's just very, very, very low concentration. All right. But these two things are kind of going back and forth. So it splits up, and then pretty quickly it goes back together. It splits up, it goes back together. Back and forth. But there's always at least a few ions that are in water. All right. When there's acid in there, it increases how much H plus there is. So there's always some, but acids have even more. All right. When there's a base in there, it increases the OH minus concentration. Okay. So if you have questions about that, you can ask either through email or when I get back. But that's kind of where this equation comes from. That's why we're allowed to use it. Okay. This other one has to do with the actual value of pH, which is the most important part. That's what we really want to be able to calculate. That's where we want to get the values from. Because if we know the pH, right, if you remember the lab we did, right, if you know the pH, they go from 0 to 14, and then right in the middle was 7. All right, values that were low on the pH scale, all right, were all acids. All right, and values that were high on the pH scale were all bases. If you were right in the middle, that meant you were neutral. So you weren't an acid or a base. So you were something like water. All right, so if we can calculate the pH of something, then that tells us if it's acidic, is it basic, is it fine, is it neutral, you know, what's going on with that value. Okay, so we're going to do a couple examples, but before we do, I want to just make a quick note, just so that I know it's in your notes. We can go over it more when I get back again if you have questions, but real quickly, some things that you could see given to you instead of H+. So sometimes it'll just straight up say, this is the H+ concentration. It could also say the hydrogen ion instead of H+. All right. It could also say, remember, proton is another word for H+. Since we know that hydrogen ions or protons usually join water right away when they're in a solution, it could also be the hydronium ion, okay, which is H3O+, so you could be given that concentration. It could be a strong acid, just like we saw in that table. HCl had the same concentration as H+. All right, this is specifically if it's monoprotic, meaning one H+ on it, and it's got to be strong, which we'll talk more about what that means later on. All right, so it has to be strong, like hydrochloric acid, and it has to be monoprotic, meaning it only has one H+. All right? But if you're given any of those things, then you can use this equation. All right? For hydroxide, it's a little simpler. All right? Either you're going to be told OH minus, it might say hydroxide, or it could give you a base, all right, a strong base like NaOH in that table before. All right, so NaOH, so it has to be a strong base, okay, and something that only has one OH minus. Okay, so it can't be something that has two hydroxides in it. Okay, but that one's a little bit easier. All right, so just so you know, any of those things would be able to use this equation. Same thing for the other one. All right, so all these things we just talked about here, all right, all of these can also be used in this second equation that we'll be talking about here. Oh. All right, if you have had logs in the past, then this shouldn't be too bad. If you haven't, then I would suggest seeking help, especially from a math teacher or from your classmates, or at least watch the calculator tutorial later on. All right, so let's do a quick practice problem. So we'll do our first one just so we can kind of see what these numbers mean. So for example, and you can even look back at the table from the notes earlier. All right, if I know my pH value is 4, then we talked about how that meant that the exponent of 10 for the H+ concentration, all right, so my H+ concentration would have an exponent, so I'd have 1.0 times 10 to the negative 4, all right? That's what this means, all right? My H+ concentration is 10 to the negative whatever the pH is. So another way of kind of rewriting the equation that's over here, all right, another way of kind of rewriting this one would be something like that the H+ concentration for anything is equal to 10 to the negative pH. Okay, that'd be like another way of saying the same thing. All right, in this case we had 4. All right, so if the question was, all right, you have a pH of 4, you know, what's your H+ concentration? Then this would be a pretty easy question to answer. If the question instead was, what's your hydroxide concentration? Then this would be an example where we want to use our first equation. All right, so we would already know that the H+ concentration is 1 times 10 to the negative 4. If I wanted to know what is my hydroxide concentration, so what's this, then I'm just going to plug and chug. So I'm going to have, all right, my concentration for H+ here is 1 times 10 to the negative 4 molar. All right, so I'm going to have here 1 times 10 to the negative 4 times my OH minus concentration, which is what I want to solve for, is equal to this constant value up here, all right, which is 1 times 10 to the negative 14. All right, if I want to get OH minus by itself, I want to divide both sides by 1 times 10 to the negative 4th. All right, divide by 1 times 10 to the negative 4th. If you know stuff about exponents, then you know you just subtract those two values from one another, those two exponents. If you don't, that's fine. Just use your calculator instead and solve the problem. You should get that your hydroxide concentration is 1 times 10 to the negative 10. All right, and again, it's a concentration, so we might make sure you have units, which in this case would be molarity. Right? So this is one example of a calculation. If you're given a pH, you can find your H+ concentration by using this idea. All right, so you might have to use your calculator if you're not sure how to do it. All right, and then you can find your hydroxide concentration using that first equation. Okay? If we were given some different information though, let's say we were given an H plus concentration, all right? So we're told the concentration of H plus is 1 times 10 to the negative 3 molar, all right? And the question is, what was the pH, all right? The pH is simply going to be the negative log, and again, you can put this in your calculator if you don't know how. Go watch the tutorial on it. All right, the negative log of the H plus concentration. In this case, 1 times 10 to the negative 3. And you should get, again, the opposite of this exponent, which is simply 3. Okay, now when they don't use nice whole numbers like how we did, it's going to get a little bit weirder, all right? So let's do another quick example here, all right? If you have an H plus concentration that's something like 2.0 times 10 to the negative 5th, let's say, okay? Then again, you're still going to put that in your calculator, the negative log of 2.0 times 10 to the negative 5th. But this time we're not going to get a nice whole number. All right, so again, if you need help using your calculator, please go watch that video. All right, but if you put 2 times 10 to the negative 5th and take the opposite log of that, you're going to get a number that's pretty close to about 4.7. All right, so notice it's close to 5. It's close to this exponent, but it's not exactly the same. All right, so for your homework, if you guys could please make sure that you go out at least 2 decimals, that would be the best. That way I would really know if you got it or not. All right, at the very least, go out to the tenths place like we did here. All right, so at least I know you know it's not a whole number. All right, don't round to whole numbers if you can help it. If your answer is a whole number, like 3, right, then by all means, you can write 3 or 3.0, but make sure you're really careful not to round too much. All right, good luck.